Thank you, Toby. So good afternoon, everyone. So today I will be talking about a new surrogate model which uses gradient information. And I will try to motivate the use of this kind of method in a design optimization by first starting a comparison between the well-known gradient-based optimization. I think many of the people who are present in the room has experience with such kind of algorithms. There are many variants of them, but the procedure is more or less same. You use the adjoint solver, you get the gradients efficiently, and then you change your design by some rule. But there are different algorithms for it. And on the other hand, there is this surrogate-based optimization methods, right? And the idea there is to you have an expensive simulation, so you cannot frequently evaluate something. So the idea is to train a mathematical model which is cheap by using a training data. And then using this mathematical model, you can afford to have many evaluations, right? And then you can use it in other optimization setting, which requires a lot of function evaluations. You can use it, for example, as well in a genetic algorithm setting, right? So there is no perfect method for all kinds of problems, right? I won't be today talking that don't use gradient base. Of course, it's not the case. There are especially high dimensional problems. Basically, you don't have much choice. If you have, let's say, 10,000 of parameters, you have to use a gradient-based methods, right? Also, in a gradient-based setting, at least mathematically, you know that it should work. Maybe you won't get the real optimum, but at least mathematically you will get you know that you will get an improvement. The problem is if you have a noise in your system, right, or you have a model response surface with many local minima, you know that you will get a reduction, but maybe the reduction is not so great because your algorithm is trapped in some local minimum, or in a local minimum very tiny generated by the noise in your system. However, you don't know whether you have noise in your system. You have just data, and usually it is difficult to make an assessment of it, right? So of course, these algorithms are vulnerable to noise. And another issue is constraint treatment may be painful in some cases, right? Many algorithms require, for example, constraint gradients. In SU2 setting, okay, at least for many objective functions, you can evaluate discrete adjoint and get the gradients. But the problem happens, for example, when you have third-party code in your evaluation chain, and you have just black box, some software, right? Well, of course, you can treat it as by using a penalty formulation and then changing the constraint optimization problem to unconstrained, but you have the pain of fixing this penalty coefficients. I mean, usually you have to give many tries before you find a good setting. Right? And of course, you have the mathematical guarantee that it will work, but your guarantee is only valid for a local optimization. However, the response surface may be multimodal, and you may be missing some other nice minima. In surrogate-based methods, right, what I will today present, they are treatable to low or medium dimensional problems. You cannot increase the dimensions so much like a gradient-based method, but okay, there are also a lot of problems out there which are low or medium dimensions. Let's say you have 20, 30, 50 design parameters, but not 10,000, right? And one advantage of this method, the method is very easy constraint treatment. So if you don't have a joint for the constraint, no problem. If you have third-party software, no problem, you can use it, right? And you have more global search in this method. Of course, there is no guarantee, right? No guarantee for convergence, not even for descent. So you try your best, and you hope you get a reduction. But it's hardly you will get an optimum, right? Other than the academic test cases. And another advantage is they are quite robust. Usually they work. You will get some solution, not the optimum, but you will get a good reduction in many cases, and you can easily parallelize. So I will very briefly mention about the surrogate model, right? The standard models as known as Kriging or the Gaussian regression model. So I have a function f, right? I want to emulate it, so the surrogate model is f tilde for some input, right? This can be your design parameters, shape parameters, whatever. And this is just a summation of basis functions by I, right? Some bunch of them, n of them, and some constant term beta 0. If your data is uncorrelated, this can be just average of your all right? As an 1D example, simple example, suppose I have 3 samples, right? These locations, x. I can use just these Gaussian basis functions centered around each sample, right? And they are perfect correlation functions, actually. For example, let's take this function here. So I have the perfect correlation one, and it just they decay very rapidly, right? And if I have 3 samples, it makes sense that I can use 3 basis functions, right? But they are radial because they are even functions, so symmetric, right? So there is no direction of change difference. Well, the question is, and this is the Kriging basis function. If you use these basis functions, you have the Kriging methods, the well-known static Kriging method. Well, then idea is how you can use the adjoint, right? Adjoint or tangent linear code, like you have in SU2, to increase the model accuracy and to get at least some local optimization character of the optimization around the sample, close to a sample. Well, the idea is here when I have gradients, right, or tangents, some sensitivity data, I can use more basis functions, and it makes sense to use the derivatives of these basis functions at some direction. So these are directional derivatives of these basis functions. So if I have n sample location, I can use standard n RBF, and then I can put also the differentiated directional derivative of these basis functions. And for the same example, you see the green curves are the differentiated basis functions. Of course, for the 1D example, you don't have much choice. Either it's -1 or +1 the direction. So, but note that they are no more radial, right? They are odd functions. They are not even functions. The nice thing is, at a sample, the green guy and the red guy, they are orthogonal to each other. So in terms of numerics, this is a good news. So you have a good condition system, and these also decay very rapidly, right? In this picture, you don't have any overlap, but normally you want some overlap because you want to interpolate. And this is the magic behind the Kriging, basically the width of these Gaussians you trained using the well-known Kriging method. What we suggest is when you have gradients, you can the best direction what you can take at this sample is basically the gradient, because at the gradient direction your function changes most, right? So we just say use di as the gradient, well, normalized directions, right? The advantage of this thing is you have in total 2n basis functions, and then at the end you have to just solve a 2n by 2n linear system, which is quite easy to train. And if you don't have gradients at some sample locations, no problem, just use less basis functions. This is of course very nice when you don't, your adjoint, for example, don't converge at some samples, right? Some configurations. I guess this problem many of you observed, that at some configuration you have a relatively okay primal convergence, but adjoint not so much, right? And all this implementation you can find in our in-house optimization and surrogate modeling toolbox Rodeo. It's on GitHub, so you can try it. It basically does two things. You can train a surrogate model and then just evaluate surrogate model values if you need it for some other study, uncertainty quantification, parameter study, etc. Or you can do the so-called efficient global optimization with it, which is a very well-established algorithm you can find in also other packages like Dakota, for example. This kind of algorithm. So as I said, this is a statistical optimization approach because the Kriging method also gives you the uncertainty of the model, so that you can do a statistical optimization. And as I said, it is, the advantage is easy constraint treatment and flexible usage. Well, how this optimization works, let me roughly sketch it. Well, of course, at the beginning, you need some training data to start with, to train your models. And for this, you need a design of experiment. So at the first stage, you just do a bunch of simulations at different samples to have the training data. Then you build surrogate model for objective function and constraints. And then using the so-called acquisition function, basically this gives you where to evaluate next in the optimization. You decide which configuration you should try next. Here is now the optimization step. So and you make you can do also generate several samples in parallel, and then at the end of the cycle you just add them to your training data and then train the model again. So at each step the model gets better somehow, and you try and at some point you stop. This is usually the stopping criterion, some computational budget. You say, I want maximum 200 simulations, that's it. And then you look what you can get. Right? Well, in this setting, we use the discrete adjoint version of SU2, right? I will show you a small hello world example in the next slide. And the surrogate model and the optimizer, they are inside our in-house tool Rodeo. Well, I think this test case is well known by everyone. It is the hello world test case for design optimization in SU2. I changed very little bit this test case, the optimization problem. Well, I want to minimize the drag coefficient of this airfoil, TPT, semi-parameterization, right? I put on area constraint, so a geometric constraint on the problem, as well as a lift constraint. So I want that the airfoil should generate lift as much as the initial airfoil, and also the area should be as much as possible so that the thing doesn't shrink. Right, and for this example, I choose 200 samples for the design of the experiment. Right. Well, this is the config. You run the Rodeo with a configuration file, very similar to SU2, and this is the configuration file for this optimization study. You see that it's not much, but Well, you just say, I want to optimize something. My problem dimension is this, but you have to give box constraint as well, the parameter limits. That's important for optimization. But anyway, for design of experiment, you need it anyway. So you give it, and then rest you just say, this is my objective. I have this constraint should be larger than this, area should be larger than that, and then you just tell where the optimizer should find the constraint on objective function values and the gradients, right? And then you can just say switch surrogate models. If you have gradients, you can say I want to use gradient enhanced surrogate model. If you don't have the gradient for some constraint or objective function, you can just skip the gradient part and use the ordinary gradient. Well, as I told you, you generate samples, right? And these are the samples for this optimization study generated in design of experiment as well as in the optimization. So in the x-axis, I have the negative minus drag coefficient, y-axis lift coefficient. Here in that picture, you don't see the geometric constraint, unfortunately. I just pick up the lift constraint. So the blue and our initial geometry is this red dot, right? And the blue dots are design of experiment samples, the initial training data, and the yellow dots, they are the samples that are generated during the optimization. So this minus CD here axis, so this part upper right, they are the good designs somehow, right? And this part, they are the worst designs. So and this line is this lift constraint. So on designs only above this line, they are feasible. Below this line, they are all unfeasible designs. And you see already for this example, already you get a good reduction in the design of experiment, and then you get even better reduction of the objective function during the efficient global optimization. Well, some of them, you see, in fact, the majority of them are unfeasible, but a bunch of samples are feasible. So you just pick up the best at the end of the optimization study. So with this slide, I conclude my presentation. Thank you very much for listening.
Hey, thank you. Are there questions for Emre?
Shall I say the question? Yeah, the question is, Lorenzo is asking which kind of boundary conditions we are using in this problem. So this is no slip and far field. This is the hello world test case when you open the tutorials in the design optimization part. This test case will be the first test. So everybody first starts with this test case. I changed just the optimization. I did not touch the SU2 config. It's the same.
Would you say that your optimization method could be affected by the boundary condition types of the flow scenario, or because sometimes we see that in this region? So since you compared it to the technologies, I was curious about whether this issue could be assessed by comparison with your method.
I did not get the question.
If you think that your optimization methodology could be affected anyway by the boundary condition selection on the flow scenario, because, for example, for discrete jumps, sometimes it happens, the convergency and numerical methods and results.
Okay, the question is, Lorenzo is asking whether the boundary conditions affects the outcome of optimization, right? The answer is of course, but that's the task of the guy who sets up the simulation process, right? The optimizer doesn't know it. The optimizer just sees the data, but doesn't know which kind of boundary conditions you are using. It doesn't even know that you are having a CFD problem. Basically, you can just give any kind of tool into this system. It can be CFD, it can be other simulation tool, whatever, right? It just sees the data.
Yes, could this workflow be integrated in such a way that it can be coupled to the FADO framework?
The question is whether this can be coupled to the FADO framework in SU2. The answer, probably yes. It could be coupled, but we kept it very general, this optimization toolbox. So SU2 is a good application field for it, but it can run with other solvers and other tools as well. That's why it's separate. So it's a software on its own.
Yeah, probably one more question.
So for your surrogate model, I know you're doing Gaussian process regression. I'm just curious, like, how many samples do you need for your data set to make it pretty robust, like, in general?
Now the question is how many samples we need so that the Gaussian process regression is robust. Yeah. Well, this is a nice question. I will say as much as possible. Of course, more richer your training data set, better the generalization of your surrogate model will be. But obviously, in many cases, you have a computational budget. So we are talking about potential applications which might be very expensive simulations, right? I saw you say, okay, I can afford maybe 500 simulations that much. I have this much resources. Then to get good generalization, you should then think of how many design parameters you are using. Usually there is a rule of thumb, the samples you use in the training data should be at least 10 times. If you have 500 simulations in your computational budget, your maximum should be 50. So you should have a parameterization with 50. But this is absolutely the upper limit. But depends on your function. If you have a smooth linear function, right? Your model can generalize with very few parameters. But if you have a wavy multimodal function with lots of details, then you need obviously more samples. But unfortunately, you don't know it.
And I guess the more like, did you use this to like kind of feedback into SU2, like be able to use their interface to like get a better state?
Sorry,
I was curious, like surrogate modeling, did you use that like as a feedback to SU2 almost to get like a better state or to converge from, or is it more just prediction in general?
it is it's separated from SU2.
Oh.
It has nothing to do with SU2. It just reads the values what SU2 generates, and that's it.
Okay. In the interest of time, I would ask you to get into Emre and the break for any further questions. So let's thank Emre again.